In the last tutorial, we learned about the Markov Decision Process, or MDP. Even though MDP by itself isn't considered reinforcement learning, much of reinforcement learning is built on top of MDP. In this tutorial, we'll get a proper introduction to reinforcement learning by studying the SARSA algorithm and the Q-learning algorithm. Both of these algorithms rely on the MDP framework and are considered foundational reinforcement learning algorithms. So what does SARSA stand for? And what is this mysterious-sounding Q-learning algorithm? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
This is the final tutorial of this machine learning series. So here's the game plan for today. We'll start by going through a quick recap of the last tutorial by getting a refresher on reinforcement learning, MDP, and the value iteration algorithm. Then we'll modify the code that we created in the last tutorial as a way to learn the SARSA algorithm and the Q-learning algorithm. Both SARSA and Q-learning rely on the MDP framework, so watching the previous tutorial is required before watching this tutorial. We'll conclude by going through a series recap to summarize everything that we've learned during the past 13 tutorials. We'll also discuss some remaining gaps in our knowledge as a way of framing potential future projects. Sound good? Okay, let's get started. In the last tutorial, we learned that reinforcement learning is an area of machine learning concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward. We also learned that a Markov decision process provides a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision maker. We learned that mathematically, an MDP is a tuple containing 5 elements: S, A, T, R, and gamma, where S is a set of states called the state space, and A is a set of actions called the action space, and T is a transition function defining the probability of transitioning to each state given the state and action at the previous time. And R is a reward function, mapping every possible transition to a real reward value. And gamma is a discount factor that defines the relative weighting of current and future rewards. We set up an MDP for an environment that we called Grid World, and fed it into a solver using the value iteration algorithm, which resulted in a policy. The policy mapped each state to an action. This policy was like a treasure map that our intelligent agent could use to follow the path that led to maximizing the reward. Even though the value iteration algorithm was very impressive, the agent didn't actually do anything to quote-unquote learn the policy. Instead, we did all of the work ourselves and then simply handed the completed map to the agent. So, that's no fun. The idea behind reinforcement learning is to release the intelligent agent into the wild, so to speak, and have the agent wander around and explore the environment to see if it can learn the best policy on its own. There are several different reinforcement learning algorithms that will allow an intelligent agent to learn on its own, but the Hello World algorithms of reinforcement learning are SARSA and Q-learning. But before we can learn about these fascinating algorithms, let's get a quick refresher on the code behind MDPs and the value iteration algorithm. We're going to modify the code from last week and set up a simplified one-dimensional grid world. For this section, knowledge of Julia and VS Code is required. Watching episode 512 is also required. In your VS Code Explorer panel, create a new folder for this tutorial. In the tutorial folder, create a new file called rl_tdlearn.jl. Launch the Julia REPL by using Alt-J, then Alt-O. Maximize the REPL panel. In the REPL, change the present working directory to your tutorial directory. Enter the package REPL by hitting the closing square bracket. Activate your tutorial directory. Add the following core POMDPs packages: POMDP Model Tools, POMDPs, and Quick POMDPs. Add the following supplemental POMDPs packages: Discrete Value Iteration, POMDP Policies, and Tabular TD Learning. Type in status to confirm the version numbers. Exit the package REPL by hitting backspace. For this tutorial, I'm going to dock the REPL panel next to my editor. Okay, let's set up our MDP for today. I'm going to go through this section fairly quickly, since this code is almost identical to the code that we used in the last tutorial. Let's start by loading some packages. Okay, now let's set up our MDP. Rather than using a two-dimensional state space like we did last week, we're going to use a simple one-dimensional state space so the agent can only move left or right. We're also going to modify the transition function slightly so that the agent will move in the correct direction 80% of the time, but 20% of the time it will move in the opposite direction. We're also going to modify the reward function by placing a negative reward of -1 in state 1 and a positive reward of +1 in state 7. Everything else we're going to leave the same. Okay, let's solve this MDP to see what the optimal policy looks like. This code is the same code that we used in the last tutorial. If you look in the REPL, you should see the policy. For this state space, we're only going to look at states 2 through 6, since both state 1 and state 7 are termination states. As you can see, all of the states have been mapped correctly to the action write for states 2 through 6. So the value iteration algorithm used an iterative process to find an optimal solution for this MDP. The agent had nothing to do with this calculation. This policy is basically a lookup table that an agent can use to find the reward. What we really want is an algorithm that the agent can use to discover this policy on its own without our help. That's what the SARSA algorithm is for. Using the SARSA algorithm is similar to using the value iteration algorithm, with some subtle differences. We start by defining the MDP using the quick POMDPs.jl package, just like before. The only difference is that we added a line for the argument called initial state, which we assigned to the state space S. Now that we've defined our MDP, we need to select a solver. The term TD learning means temporal difference learning. TD learning algorithms are reinforcement learning algorithms that learn the value function by sampling from the environment. Both SARSA and Q-learning fall under the TD learning umbrella, so these solvers are located in the tabular tdlearning.jl package. Using a random seed is not required. I'm using it so I can reproduce my results. Like other machine learning algorithms, the SARSA algorithm uses a learning rate, denoted by the lowercase Greek letter alpha. I'm using a value of 0.9, but you can use any value between 0 and 1. The SARSA algorithm uses something called an episode. I'll explain what that is in a minute. We're going to start with a value of 1 and then change it later to see the impact. We're using a solver appropriately named the SARSA solver. SARSA stands for State Action Reward, State Action. The way that this algorithm works is that the agent wakes up and finds itself in some state S, which is mapped to some action A with a reward value of R. This initial position has some action value called Q. The agent then takes one step using the action A and finds itself in a new state, S', which is mapped to some new action, A'. Based on the information that the agent has learned from just this one step, the algorithm can then estimate the value of the entire policy. Using this estimate, the algorithm then updates the action value Q from the original position. This Q value from the previous position is updated after every step. When deciding how to take that one step, the agent ignores the transition function. Instead, it uses something called the E-greedy policy, which is short for epsilon greedy policy. Epsilon is the probability of the agent going off in some random direction, while 1 minus epsilon is the probability that the agent will follow the action which leads to the highest reward based on the latest and greatest information. By using a value of 0.5, that means that the agent will follow the action mapped to the state 50% of the time, and the other 50% of the time, it will pick a direction at random. In reinforcement learning, this random movement is called exploration, while moving based on the best available information is called exploitation. When designing reinforcement learning models, the goal is to find a balance between exploration and exploitation. The term episode means the entire journey from some initial state to a termination state, regardless of how many steps that takes. So by using a value of 1, that means that our agent will wander around in the state space until it reaches either the negative reward in state 1 or the positive reward in state 7. The SARSA algorithm is considered an on-policy learning algorithm, meaning that the policy that our agent is trying to learn is the policy that it's actually following. The SARSA algorithm is updating the estimated policy at every step, and not waiting until the agent completes a full episode. Let's solve this and see what the estimated policy looks like after one episode. If you look in the REPL, you'll see the estimated policy. The actions are all pointing to the left, which will result in a negative reward of -1. Left is the default action, so it appears that our agent didn't actually learn anything after just one episode. Let's increase the number of episodes to 10, and then take another look. So it looks like our agent is starting to explore, but it still has a lot to learn. Let's increase the number of episodes to 15, and then take another look. Okay, so it looks like our agent nailed it. This estimated policy that our agent figured out by using the SARSA algorithm is identical to the policy that we calculated using the value iteration algorithm. And our little agent did it all by itself, without any of our help.
Bruh.
Pretty cool, right? Now let's take a look at the Q-learning algorithm. The code for implementing the Q-learning algorithm is almost identical to the code for the SARSA algorithm, but it's doing something slightly different under the hood. Since the code for the Q-learning algorithm is similar to the code for the SARSA algorithm, you can just copy and paste the code from above, starting with a header. Then, just change all of the references for SARSA to references for Q-learning. Just like what happened the first time using the SARSA algorithm, it appears that our agent didn't actually learn anything after just one episode of trying out the Q-learning algorithm. Let's change the number of episodes to 10 to see what happens. Similar to our experience using the SARSA algorithm, it looks like our agent is starting to explore using the Q-learning algorithm. Let's try increasing the number of episodes to 15 to see what happens. So this is different. When using the SARSA algorithm, our agent was able to estimate the correct policy after 15 episodes. But when using the Q-learning algorithm, it looks like our agent has figured out most of it, but hasn't quite figured it all out yet. Let's increase the number of episodes to 20 to see what happens. So it looks like our agent finally got it. Pretty cool, right? It took a little longer for our agent to find a solution using the Q-learning algorithm compared to the SARSA algorithm, but it finally got there. So, what's going on? Unlike the SARSA algorithm, the Q-learning algorithm is considered off-policy learning, meaning that the agent is following the behavior of some other policy and using that knowledge to learn the optimal way to behave in its own environment. When deciding on a next action to take, the Q-learning algorithm uses a behavior policy that is different than the target policy. But when calculating the update to the Q action value of the original state, the Q-learning algorithm uses the next action that would have been taken using the target policy. In other words, when using the Q-learning algorithm, the agent is always exploring when taking steps. But when it comes to updating the Q action value, the agent is using a more conservative approach. Intuitively, this may not make any sense, but mathematically, it turns out that this approach leads to the optimal action value function, or Q function. By contrast, the SARSA algorithm is really just estimating, so the solution it finds may not necessarily be the optimal solution. Because the Q-learning algorithm is more sophisticated, it may take longer to converge on a solution, but the solution it finds will be the optimal solution. In our simple one-dimensional example, it really didn't matter that much, but keep this in mind as you scale up your projects by creating more complex environments. The SARSA algorithm works great for simple environments, but as your environments get more complex, consider using the Q-learning algorithm. So that does it for the code. There wasn't a lot of new code in this tutorial, but there were a lot of new concepts. So let's go through a recap of what we just learned. After getting a quick refresher on setting up an MDP and solving it using the value iteration algorithm, we were reminded that the value iteration algorithm is not considered reinforcement learning, since the agent didn't actually learn anything on its own. In order for our intelligent agent to learn how to move around in our environment, we used two temporal difference learning algorithms known as SARSA and Q-learning. SARSA stands for State Action Reward, State Action. It's a simple algorithm that learns as it goes and updates its knowledge after every step. It's really just estimating, so the solution it finds may not necessarily be the optimal solution. Q-learning is a generalization of SARSA and is the reinforcement learning equivalent to the value iteration algorithm. Q-learning applies an interesting approach to learning by taking actions based on an exploratory policy, while updating values based on an exploitation policy. Although this may be counterintuitive, the Q-learning algorithm will eventually converge on the optimal policy. those are some heavy concepts to digest. So let's stop here. It seems like I covered a lot, but I barely scratched the surface of the PalmDPs.jl package. When you get a chance, please show your appreciation to the entire team working on the PalmDPs.jl package and ecosystem by going to the GitHub page of PalmDPs.jl and be sure to leave them a star. Let's go back to the Wikipedia article on machine learning and see how we did. By now, you should know what machine learning is, and you should know the difference between supervised, unsupervised, and reinforcement learning. If you expand the section under supervised learning, you should now be familiar with most of those algorithms. As for unsupervised learning, we covered clustering and dimensionality reduction. But if you expand those sections, you'll see that there are a lot of algorithms that we didn't cover. As for reinforcement learning, there aren't that many algorithms listed there. In fact, we covered most of those algorithms in today's tutorial. Reinforcement learning is a rapidly developing field, so I suspect there will be many more algorithms listed there in the years to come. Artificial neural network is an interesting section. We did cover the multi-layer perceptron during the Flux.jl tutorials, but for the most part, I didn't cover this subject since many of these algorithms are considered deep learning algorithms. I did not cover structured prediction or anomaly detection at all. But as a free bonus, we learned about the Markov decision process and the value iteration algorithm. So we covered a lot of algorithms, but we also skipped a lot of algorithms. Machine learning is an enormous field of study. For some of you, this series may have been too much. But for others of you, this series may not have been nearly enough. Machine learning is definitely a challenging subject to cover, and the best that I can hope for is that this series has equipped you with a solid foundation in the core concepts and core algorithms so that you can feel comfortable pursuing the subject further on your own. As for me, I think I'm done covering supervised learning. It's true that I didn't cover all of the algorithms, but I suspect that you'll be able to learn them on your own without my assistance. As for unsupervised learning, I barely scratched the surface. I found this subject to be very interesting, so I may make more tutorials on unsupervised learning in the future. The same goes for reinforcement learning. I really just provided a glimpse into reinforcement learning, so I'd like to make more tutorials on reinforcement learning in the future. As for deep learning, I provided a brief introduction to it by using the Flux.jl package, but I'm hoping to make a separate 13-part series on deep learning in the future. PalmDPs is another interesting subject. Even though we use the PalmDPs.jl package, I didn't actually cover PalmDP. PalmDP stands for Partially Observable Markov Decision Process, and it's a generalization of MDP. But I don't feel compelled to make a series on this subject, since there's already an excellent playlist for the PalmDPs.jl package on Julia's official YouTube channel. Nevertheless, it's a fascinating subject that I would like to spend more time exploring. The PalmDPs.jl package also supports deep reinforcement learning, which is another emerging field that I'm interested in. What about you? Are there other subjects that you'd like me to cover in the future? Let me know in the comments below, and I'll add them to my ever-growing to-do list. You did it! This was an extremely difficult 13-part series, so if you made it through all 13 tutorials, Congratulations! As I've done in the past, I will be going on a brief hiatus for a few weeks to start preparing for the next series. That's another way of saying that I'll be catching up on my sleep. I would like to thank all of you for watching, and I would especially like to thank my channel members. Your support means a lot to me, and it motivates me to keep creating new content. I cannot thank you enough. Take care, everyone, and I'll see you again in a few weeks. Bye for now.